Hello, and welcome to Business Calculus, Solving Inequalities Using Continuity Properties. One of our best tools for analyzing functions and their graphs is called a sign chart. Sign charts take advantage of continuity properties to allow the easy tracking of whether a function is positive or negative over an interval. Suppose we have a function f that is continuous on the interval from 1 to 5. And we also know that the function is not equal to 0 anywhere on this interval. If we also know that the function when x equals 2 is equal to 1, is it possible that f of x is negative for any value x between 1 and 5? The answer to the previous question is no. The reason for this is continuity. If we look at the figure on the right, we ask ourselves, is it possible to draw an unbroken curve that connects the 2 points, passes the vertical line test, and does not cross the x-axis? And try as you might, it's absolutely impossible. What this does is it yields the following condition that we can use to solve problems. If f is continuous, and f of x is not equal to 0 on an interval from a to b, then f of x cannot change sign on the interval from a to b. What we would like to do now is to solve the following inequality. In order to do that, we are going to construct a sign chart. And the way that we do that is as follows. The first thing that we want to do is determine the values of x where the numerator is equal to 0 and where the denominator is equal to 0. We see that x equals -1 causes the numerator to be 0, and x equals 4 causes the denominator to be 0. Using these two values, we are going to draw a number line. And we're going to plot these 2 points along that number line. I'm going to use a filled-in circle for -1 because it made the denominator or the numerator equal to 0, and I'm going to use an open circle for 4 because it made the denominator equal to 0. We use an open circle for 4 because it is not in the domain of the function, whereas -1 is. Okay? The next thing that we're going to do is select a number of test points in each of these intervals. And I will go ahead and signify these intervals in interval notation, just so it's clear what we're talking about. We have the interval from -∞ to -1, from -1 to 4, and from 4 to +∞. What I would like to do is pick a value between -∞ and -1, not choosing any of those actual values, and plug it into my function. I'm going to pick -2 because it's an easy choice. By evaluating this quantity, we see that we get -1 divided by -6, which is equal to 1/6. And this value is greater than 0. Because this value is greater than 0, we're going to put a plus sign above this interval to signify that this is where the function is going to be positive. Next up, I select a value in my second interval from -1 to 4, and I'm going to pick 0 because 0 is always easy if we get to pick 0. We plug the number in. We see that it makes our arithmetic go very, very quickly, and we get a value that is less than 0. So we signify that the function is going to be negative along that interval. And lastly, we plug in a value between 4 and +∞, and we're going to select 5. We get 6 divided by 1, which is equal to 6, which is a positive value. And so we write here that the function is positive on the interval from 4 to infinity. Now, going back to our original expression, we want to know the values for which x plus 1 divided by x minus 4 are positive. So we look at our sign chart and we see that our plus signs lie in this interval and this interval. And we see that we want a strictly greater than, so we don't want to include when it's equal to 0, and that allows us to say that the answer to our question is the interval from negative infinity to negative 1 union 4 to infinity. In our next example, we want to do the same kind of thing. We want to know for what values of x is x squared minus 4 divided by x plus 1 less than or equal to 0. And we're going to do the same thing. We're going to figure out the values for when the numerator is equal to 0 and for when the denominator is equal to 0. We can factor our numerator and see that it is equal to 0 when x is equal to negative 2 and 2. And we can see that our denominator is equal to 0 when x is equal to negative 1. Next up, we draw our number line large enough to make sure that we have room for everything. We're going to put a point here for negative 2. We're going to put an open circle for negative 1 because it came from the denominator. And then over here, we're going to put a filled-in circle for positive 2. Our intervals for this problem are negative infinity to negative 2, negative 2 to negative 1, negative 1 to positive 2, and positive 2 to infinity. Now we do the same thing that we did before. We pick a point in each interval, test it, and determine if the function is positive or negative on each piece. We're going to be selecting negative 3 out of our first interval. And we see that negative 3 squared is 9, and 9 minus 4 is 5. In the denominator, we have negative 2, and we see that this value is less than 0. So we put a negative sign up here. Next up, we need to pick a value that's between negative 2 and negative 1. So we're going to pick negative 3 halves. In our numerator, this is going to give us 9 divided by 4 minus 4, which is going to be negative. And in the denominator, we have negative 3 halves plus 1, which is going to be negative 1 half, which is also negative. We have a negative divided by a negative, so that means that this value is positive. We don't need to know the actual value so long as we can determine whether or not it's positive or negative. Since I have a negative number divided by another negative number, that's sufficient. Next up, we're going to pick a value in the interval between negative 1 and 2. And this is the best interval because it's the one that contains 0. So we plug in 0 to our function. We get negative 4 divided by 1, which of course is negative. And we lastly evaluate the finer interval by picking a value. We'll say 3, plugging it into our function, and we're going to get 5 divided by 4, which is positive. Okay? Now, we are interested in the intervals where our expression x squared minus 4 over x plus 1 is less than or equal to 0. Okay? So if we look at our sign chart, we want the parts that show up as negative. We need to be a little bit careful here because this says less than or equal to, so we're going to go from negative infinity to negative 2, but we're going to use a brace to show that we're including the value negative 2, and we're going to take the union of the other interval from negative 1 to 2. Now, we need to skip -1 and not include it in the interval because -1 is not in the domain of this function. Since it makes the denominator equal to 0, that open circle reminds us that we can't choose that value. However, we can choose +2. So the solution of this problem is -∞ to -2 inclusive, union -1 to 2 inclusive. Now, what we've lined out here is a list of 4 steps that will allow you to construct your own sign charts. If you're given some function f, you want to find all of the partition numbers. And the partition numbers we were finding were the values of x that make either the denominator or numerator equal to 0. You plot the partition numbers on a real number line, dividing the line into intervals, and then you choose a value of x from each open interval that we found in step 2 to determine if the function f is positive or negative in that interval. Lastly, you indicate with plus or minus signs if the function is positive or negative, and then answer your final question based on those results. Now what I would like for you to do is solve the following inequality using your own sign charts. Here are some potential answers. Thank you very much for your time.